welcome you all in this class. And in the last class, we started our discussion on fins, and we introduce you. We discuss the application of fin and what is and why fins are important in the transfer of heat. This is unit 2. We are currently in unit 2, and this is lecture number 2 of this unit. So the objective uh, of our present lecture is to identify the applications in which insulation may actually increase the heat transfer. There are some applications where insulation may actually increase the heat transfer. Then analyze the finned surfaces and assess how efficiently and effectively fins enhance heat transfer. Solve our multidimensional practical heat conduction problem using conduction shape factor. So these are the objectives of the present lecture. So in the last class we started the fin with the introduction of fin, and fins are the extended surfaces from any body which are used to increase the heat transfer rate from the surface from the surface. Okay. We have seen in many applications, like in the like in the compressor or refrigerators, and compressors of refrigerator, and many other parts. There are many extended surfaces. Those extended surfaces are called the fins. Okay. That is why there are two ways to increase the heat transfer rate by convection. One is the increasing the by increasing the heat transfer coefficient. Okay, but increasing the heat transfer coefficient may not be sufficient to increase the large amount of heat. So another way it is to use the fin actually increase the surface area. Okay, surface area of which heat can be transferred to the surrounding. Okay, from the Newton's cooling law, we know HA into delta T. Okay, so one way is to increase the heat transfer coefficient, and another way is to increase the area. Okay, so if we increase the area, we can again be able to increase the heat transfer rate through convection. Okay, for example, if we look at this figure, in this figure, as you can see, the heat is this is the hot surface. Okay, where the temperature is very high. So within this if you look at this plate, within this plate, heat will be transferred through the conduction. Okay, so the surface available for the conduction will be this one. Okay, so and if we add this fin on this surface, so what will happen, that the heat will be conducted throughout this body, and throughout this surface heat will be you can see will be transferred to the atmosphere through convection. Okay, so heat transferred through the convection is increased because the area of the surface from where the heat can be from where is increased. Okay, so this is how the heat is transferred through the convection. Okay, so if we take a elemental a volume element whose length is delta x, okay, which is at a distance x from the surface, and let's say that A is the cross sectional area. Cross sectional area means that which cross sectional area which is perpendicular to the direction of convection. Okay, direction of conduction. Okay, so if we analyze this elemental volume, what we see that heat is entering from one plate through conduction, and leaving from one surface through conduction, but as well as heat is also leaving this volumetric area through the convection. Okay, so if if we look at this figure, we can say that rate of heat conduction into the element X. Okay, the rate of heat conduction, this heat entering into the element is basically leaving in two ways. One is by conduction and another way is by convection. Okay, so rate of heat conduction into the element at X will be the sum of rate of heat conduction from the element at X plus delta X. Okay, means from this surface, and plus the rate of heat conduction from the element. Okay, heat convection from the element. So heat will be leaving this volume, this is elemental volume, by the conduction as well as by the convection. So this is by the convention, where A is the area of cross section, and P we will this is one more parameter, P is called the perimeter. Okay, perimeter will be another important parameter that we will be using in this analysis. So, fin equation from the previous slide, as we can see, can be written as rate of heat transfer in terms of symbols, rate of heat transfer, heat entering into the volume element at X, and rate that is equal to rate of heat leaving the volume at X plus delta X, and rate of heat convection. Okay, from the volume element. Okay, so this is the this will be the equation. Now rate of heat convection, rate of heat convection, or you can say the heat leaving the surface by convection will be given as H into area. P into delta X is the area of cross section. Okay, so the area of cross section is given as P in, area uh, P into AX. Okay, this is the area from where the heat is leaving through convection. Okay, and and this area is different from the area of cross section. Okay, this is different from AC, that the symbol AC that we used for the for our in the previous slide. It is different from the from the AC. Okay, from through AC, the area the cross sectional area conduction is taking place. Okay, and then T minus T infinity, where T is the temperature of the volume element and T infinity is the ambient temperature. Okay, so if we rearrange this equation in this way, that we bring this part here on this side. So what will happen? Rate of heat conduction at X plus delta X minus rate of heat conduction at X divided by delta X, by dividing a whole equation by delta X, plus putting this convection value over here. So what we will get? HP into T minus T infinity. Okay, by after division with the delta X, this delta X will be cancelled over here. Okay, so HP will remain here equal to 0. So this is the equation that we will get. And if we take the limiting case, that is X tending to 0, we apply the concept of limit over here. So what we get? Delta Q dot conduction upon this this value, if we take the limit, this value will be converted into this value. Okay, del Q dot upon dq dot upon dx plus HP T minus T infinity, HP T minus T infinity equal to 0. Okay, where Q conduction, as we all know from the Fourier's law, that conduction heat transfer is equal to minus KAC dt over dx. Okay, this is the area of cross section. Okay, and P into delta X, and P into delta X is different from cross sectional area. Okay, so this is the area through which convection is taking place, and AC is the area through which conduction is taking place. Okay, so this we have to keep in mind. So heat conduction is minus KAC dt over dx. So by putting this value over here, what we get? We get d over dx KAC or dt over dx minus HP T minus T infinity equal to 0. Now this equation can be further written in this form, where theta equal to equal to uh, t minus t infinity. Okay, where theta equal to t minus t infinity, and and if we differentiate this part, if we differentiate this part, what we will get d theta equal to dt. So in the place of dt over dx, we can write d theta over dx. Okay, that will become d2 theta over dx square, and in the place of this value, we can write theta, that is equal to theta. And after dividing this whole equation, after dividing this whole equation with KAC, okay, divide this whole equation with KAC. So here k, if we divide KAC, and again here divide this part with KAC, okay. So what will happen, that we will get this final equation. Okay, this is the equation that we will get when we divide this equation, where m square in this equation, m square is nothing but this value. M square is hp upon KAC. Okay, hp upon KAC, the okay. So this is the basic equation, and it tells, this is a differential equation, and it tells about the temperature excess on the finned surface. So the general equation of general solution of the differential equation is in a general solution of this differential equation. The equation that we derived previously is this one. Okay, if we solve this equation, then we get the equation in this format: theta is x equal to c1 e to the power mx plus c2 e to the power minus mx, and and again, as you can see, it consists of these two unknowns. Okay, c1 and c2. So in order to solve this equation, in order to solve this equation, we need the values of c1 and c2. Okay, so again, this equation can be solved by using defining the boundary condition at the fin base and at the fin tip. Okay, so the first boundary condition that we can define is the fin condition at the fin base. Okay, this is the this is where we can define the our condition very easily, the condition of the fin very easily. So as you can see, this is the case. This is this is a fin. This is one type of fin where we can define the boundary condition. Okay, and what is the what is this kind of fin? This is the fin. I mean, in order to solve this equation, we need boundary condition at two places: one at the fin, and at the and also the boundary condition at the tip of the fin. Okay, so here at the base, the fin has a specified temperature. Okay, and from the base, the heat loss is negligible. The heat loss is negligible, and convection, these I mean, these are the cases where with respect to which we can define the boundary condition. Okay, so the first case is that the fin is infinitely long. Okay, fin is infinitely long. At the base, this is the boundary condition for in all cases, but at the tip, the boundary condition may vary depending upon the situation at the tip. So we have to look case by case. So okay, so let's say that at for the infinitely long fin. So for the infinitely long fin means that since it is very long, so we can safely say that the temperature at the tip will be equal to the ambient temperature. Okay, so the boundary condition at the tip will be equal to this value. Boundary condition at the tip will be equal to this, where at theta L, theta is T minus T infinity. Okay, so theta at L can be written as TL minus T infinity. Okay, temperature at the tip minus ambient temperature. Okay, and since at tip in this case the TL will be equal to T infinity, as L tending to infinity, so there is no difference, the temperature difference between tip and the atmospheric temperature or ambient temperature is 0. Okay, or negligible. So this is the one condition that will remain same in all the condition, all types of fin, and this is the one condition that we obtained for the infinitely long fin. Okay, so in order to solve the problem involving or infinitely long fin, these two boundary conditions can be safely utilized. Okay, now after utilizing the boundary condition, this is the this is the solution of the equation B get. Okay, so this is Tx minus T infinity upon Tb minus T infinity equal to e to the power minus x, that is equal to e to the power minus x Hp upon Ka, where Tx is the temperature at the distance x from the base. Okay, from the base, and T infinity is the ambient temperature. Tb is the temperature at the base, base. Okay, and T minus T infinity is this is what theta that we got. Okay, so you can say this equation you can also write in this form, that you can say theta equal to theta upon theta b. Okay, theta upon theta b, as is it has been discussed in the previous slide as well. So theta minus theta infinity, and m is the hp upon Ka, where m we have earlier described that m equal to under root hp upon Ka. So the steady rate of heat transfer from the entire fin, for the steady rate of heat transfer, this is the temperature distribution. This equation that we have obtained is for the temperature distribution. In this m equal to hp upon Ka. Now the steady rate of this is the temperature distribution that we have found. The next step is to find the heat transfer rate from the entire fin. What is the amount of heat that is being transferred by the entire fin? Okay, so how it can be found? It can be found by utilizing this equation. And we know what is the temperature distribution, dt over dx we have already got to know. So this heat transfer from the entire you can see entire surface will be equal to hpKa upon into Tb minus T infinity. This is how the heat transfer rate can be found out. In dt over ds, the value of dt over ds at x equal to 0, can be found out, found out from the slide, from the values given in the previous slide. So and this is how the heat transfer rate can be calculated. This is the amount of heat that should be transferred, that should be transferred from the fin to the surrounding. Okay, and this heat is basically generated at the base of the you can say fin. Okay, this heat is entering at the base of the fin. Okay, so this is the amount of the heat that has to be that will be transferred from the fin. So as you can see, this is how the temperature varies with distance. Okay, as the heat you can see that that the temperature is not uniform on the surface of the fin, but it varies along the surface of the fin. Okay, so the temperature here is the maximum, and then it goes on decreasing, and the temperature at the tip is always a minimum. Okay, so this is the variation of temperature as we can see here. If this is a cylindrical fin, and so that temperature varies in this way. This is in this way. So under steady condition, heat transfer from the exposed surface is equal to heat conduction to the fin at the base. The rate of heat transfer from the fin could also be determined by considering heat transfer from a differential volume element of fin, integrating it over the entire surface of the fin. So the fin Q of the fin can be found out H into Tx minus or T infinity into D area, elemental area of the film, equal to so this equation will come up. Okay, and this is the variation of the temperature that is shown here, and you can see this is the equation. This is the line will follow this equation. X equal to T infinity TB minus T infinity e to the power minus x h under root HP upon KAC. HP upon KAC is basically M. Okay, and P is in this case pi d, and AC is pi squared d by 4. So that was the case of infinitely long fin. Now there may be another case where the fin might the fin might be insulated from the on the tip. Okay, that is called the negligible heat loss from the fin tip, or you can say adiabatic fin tip, where q fin equal to fin tip equal to 0. Okay, it means that from on the tip the heat transfer rate from the tip equal to 0. Okay, so again in this case what will happen, the tip will be at the specified temperature, the negligible heat loss, the convection and radiation will be the mode of heat transfer. Okay, so at the tip these condition will exist. Again at the base the temperature is properly predefined, and the same conditions that one boundary condition from the on the base will remain same in all the cases. Okay, so fins are not likely to be so long that their temperature approaches the surrounding temperature at the tip. A more realistic assumption is for the heat transfer from the tip to be negligible, since surface area of the fin tip is usually a negligible fraction of the total fin area. So the boundary condition at the fin tip can be taken. Boundary condition at the base is same in all cases. Okay, so boundary condition at the fin tip is dt over dx at x equal to L equal to 0. Okay, because the no heat is being transferred to the surrounding, it means that that the temperature gradient equal to 0. The temperature gradient is 0. Okay, because the heat transfer is very less, so we can say that dt over dx is 0. So d theta over dx at x equal to taken as 0. Temperature is not 0 in this case, but the gradient of temperature is 0. So the variation of temperature along the fin, along the long fin, can be given using this formula. After solving the equation of the fin, we get this equation, and heat transfer from the entire fin can be found. This is the this equation actually gives the variation of temperature or distribution of temperature along the fin surface. Okay, and this equation provides the heat transfer from the heat transfer from the entire fin, and this is equal to HPKAC into TB minus T infinity tan ml. Okay, tan h, where h is the hyperbolic function. Okay, tan h is the hyperbolic tan h, hyperbolic tan. So another case can be specified temperature, that the temperature of the fin is known, temperature of the fin tip is known. Okay, and how it is known? It is different from the ambient temperature. So there will always exist some kind of temperature difference between the fin tip and the atmospheric temperature. Okay, so in this case the temperature at the end of the film, the fin tip is fixed at a specified temperature TL. This case could be considered as the generalization of the case of infinitely long fin, where the fin tip temperature was fixed at T infinity. Okay, so the boundary condition at the fin tip can be taken as this at x equal to L, theta equal to theta L, and TL that is equal to TL minus T infinity. Okay, in this way we can proceed for the solution of the general equation of in this way we can proceed for the solution of general equation of fin surface. Okay, so specified fin temperature, after solving the equation we get this long equation. This is the long equation that will give the temperature distribution of the fin. Okay, so this is a big long equation, and if we simplify this equation and we put TL equal to T infinity, then we will get we will get the solution of the our first case. Okay, so again the heat transfer in this case will be calculated using this formula. Okay, that is equal to HP KAC into TB minus T infinity cos cos ml minus TL minus T infinity upon TB minus T infinity upon sin ml. Okay, again if we put TL equal to T infinity, then what will happen, that this part will disappear. This part of the equation will be equal to 0, and what we will get that we will get cos HML and sin HML, sin HML. Okay, so basically it will be some for it will be again the heat transfer rate, simplified form of heat transfer rate at when the fin tip temperature is equal to the temperature of the ambient. So this is the another case where the convection is taking from the fin tip, that the convection cannot be ignored in some cases. So what will happen, that the fin tips in practice are exposed to the surrounding, and thus the proper boundary condition for the fin tip is convection that may also include the effect of radiation. Consider the case of convection only at the tip. Condition at the fin tip can be obtained from an energy balance at the fin tips. Okay, so heat transfer due to convection is heat transfer due to the conduction, and boundary condition at the fin tip can be taken like this. Okay, these are the boundary condition at the fin tip: minus KAC dt over dx at x equal to L equal to HAC TL minus T infinity. So the convection from the convection at the tip, so this is the solution of the equation, and this is the temperature distribution that we get when we consider the convection from the fin tip. Okay, this is the equation that we get. Then for the convection from the fin tip, this is the fin tip, this is the rate of heat conduction is equal to rate of heat conduction, as we have discussed in this case. So the solution of this general equation will be this long. Okay, this is the solution of general equation sin h. Okay, as you can see that this term is always remains same in all cases. Okay, only this part of the this part varies, only this part changes every time. Okay, so we can see from here that this is the heat transfer of rate of when the convection is taken from the fin tip. So this is the sometimes what happens, that heat loss from the fin tip is to replace the fin length L in relation to insulated tip case by a corrected length. Okay, if there is some kind of insulated fin tip, what we do, we utilize this concept of corrected length. Okay, where LC equal to where is called the corrected length, and that is equal to L plus AC upon P. So the correct rectangular fin for the rectangular fin, corrected length will be L plus T by 2, and for the cylindrical fin, L plus D by 4. So T is the thickness of the rectangular fin, D is the diameter of the cylindrical fins. Okay, so in both cases these are the corrected lengths that can be utilized for the solution of this problem. Okay, so this is the corrected length. Okay, and corrected length is defined in such that LC with insulated tip is equal to the heat transfer from the actual fin of length L with convection. So the summary of the present lecture is shown here. We studied the steady state conduction, we studied about the thermal conduct resistance, and we further studies about the fin, the application of fin, and we derived the equation of fin in this lecture. So these are the review question that you can attempt at your home. So these are the references from where the material for this lecture. These are the books you can refer to for reading purpose. Thank you for attending this lecture. Thank you all.